Okay, today we're going to work with trig relationships and working with trigonometric expressions, simplifying and combining so that we can do more algebra with trig. The main thing that we need to know here is that when you work with sines, well, you got to know how to work with sines, right? Check it out. You also got to work with cosines and tangents and all those things. But basically the idea here, back to this, is that sine theta is simply a number, right? It's a number, and therefore, since we don't know what it is, we can think of it like a number that we don't know what it is, better known as a variable. So if we think of sine theta, the whole thing, as just like an x, then we can work with it exactly like we would work with an x. So, for example, sine theta plus sine theta is simply 2 sine theta. 5 sine theta minus 12 sine theta, negative 7 sine theta. Now here's one where we've got 5 sine theta minus x sine theta. Well, the 5 and the x are different, but the sine theta is the same. It's a common factor. There's a multiply here, and so we can factor the sine theta out and get 5 minus x sine theta. Here's another thing to know. When we multiply two expressions that involve the same trig function with the same argument, we get 5 times 4 is 20, and sine theta times sine theta is just sine squared theta. There are some things that are not true, and I just want to draw your attention to some of the things that aren't. When we take sine theta and add sine 2 theta, we don't add the arguments. We don't add them together. It's just like if you have x squared, and then we add, 2x squared. That's not equal to 3x squared. You have to do the squaring first to get x squared here, and when you do the squaring of 2x, you get something else. You get 4x squared, right? So this is not 3x squared. It's something quite different. So we don't add the arguments. Here's another real common one. Sine of theta plus t, or a plus b, or whatever you want to call it, is not equal to the sine of theta plus the sine of t. Sine is not a multiply. We can distribute multiplication. If we had a times theta plus t, if this was a multiply here, then we get a theta plus at. That's fine. No problem there. But sine is not a multiply. It's a function. This is sine of x, not times. We can't take sine and just say, oh, what's sine times cosine or something. They don't exist. Sine and cosine need an argument to have the function. So theta is an argument, not a product. Here's another example. We don't want to mess with the arguments. Suppose, for example, I take sine of 4x plus 3 and I multiply by the sine of 4x plus 3 again. What do I get? Right? Plus 3. Well, the 4x plus 3 is all inside the argument. This is what's going into sine. What comes out is this thing. That's a number. That's a number that comes out of there. This is that same number that comes out of there. We don't mess with this inside stuff. We get just the product of these two numbers, which is sine squared of 4x plus 3. And that's how we work with that kind of thing. Okay, let's look at a couple of examples. We'll start with a couple of simple ones. 3 cosine theta plus 4 cosine theta right here is simply 7 cosine theta. Again, treat the cosine theta like a variable. It's a number. We don't know what it is. We have 3 of them. We have 4 of them. Add together, we get 7 of them. Likewise, sine of alpha minus 3 sine of alpha is just minus 2 sine of alpha. So those are the kind of fundamentals there. Now we're going to start introducing some identities, and I want to remind you what an identity is. It's a relationship that's always true. An equation such as, a times b plus c is always going to be equal to ab plus AC, or 1 times x equals x. Those are identities, and we can use them to rewrite equations and make them more familiar. So it takes a lot of practice with trig, and there's lots of identities, and it gets really fun actually if you like algebra and you like this kind of thing. But probably the most useful identity in trig is the fundamental one. It's called the Pythagorean identity, which I call the big kahuna. And it simply says that sine squared plus cosine squared of any angle is 1. And that comes from our unit circle. If you remember, our unit circle, we have a radius of 1. We have a sine of some value. This is sine of theta, that height. There is sine of theta if this is the angle theta. And cosine of theta is this x value, cosine theta, right? And the Pythagorean theorem tells us that sine squared plus cosine squared is equal to 1, which is always going to be true. So that's a big one to look for. We can, of course, rewrite this in various ways. If you take a look at this here, we've got sine squared in terms of cosine squared in terms of sine squared. And really, the idea here is more important than memorizing any of these. The idea is if you have an equation that involves both sine squared and cosine squared, usually it's easier if you can eliminate one of those and change it into the other. And so we can do that using substitutions like this and turn the equation into one that has only one trig function, and then it's easier to solve. So let's look at a few examples of how we might use this. 2 minus 2 sine squared theta. If we take a look at that, we can hopefully notice that there's a 2 in both of these. And of course we're going to use our friend factoring, so we can factor out the 2 and say that's 2 times 1 minus sine squared theta. And lo and behold, 1 minus sine squared theta is cosine squared theta. So we really have 2 cosine squared theta as a simpler way of writing it. Here's another one, and there's a couple ways to do this. One way would be to take this, and since this is equal to cosine squared, we could put that in there and then multiply it out, and we'd have an equation that just involves sine squared. Or actually it'd end up with some sine cubed and various things, but it would just have sines, no more cosines. But if you look at it more carefully, it's actually easier to do this by factoring. You see a common factor of sine theta. There's one, and there are 3 of them here. So I can factor out the sine theta, and I do this, and what do we have? Well, this sine theta is times a cosine squared, so I write cosine squared theta, plus, what do we multiply sine by to get sine cubed? Well, we need another sine squared. We need 2 more powers, so sine squared of theta. And then, of course, this is 1. We see that. That's our Pythagorean identity. And this whole thing just simplifies down into sine theta. Those are the kind of really nice simplifications that can occur when you really know how to use identities with trig functions. Okay, let's look at a couple more of these. Starting with cosine theta minus sine theta squared. This is a parentheses. We've got to FOIL it. So we're going to do, using that pattern, this is a squared plus 2ab plus b squared. So we'll take the first term squared, that's cosine squared theta. And then twice the product of the 2 terms, and there's a minus sign here, so it's minus twice the product of those 2, cosine theta, sine theta, and plus the second term squared, which is going to be sine squared theta, like that. And now we take a look and see what else we can do, and if you're astute, you'll notice that we've got cosine squared plus sine squared, and that's equal to 1. And so we call this 1 minus 2 cosine theta sine theta. And that's a nice, simpler way to write this. We don't have a square anymore. We still have both cosine and sine, and if we wanted to, we could replace one of them with the other, although we'd have a square root because we only have an equation for squares right now. But we'll see that there are lots of other things to do with this as we move on. All right, let's take a look at some of these. 3 tangent x minus sine x over cosine x. Well, we're going to use the idea that this sine x over cosine x is tangent x, right? So sometimes we'll need to do that. And we've got 3 tangent then minus 1 tangent, and that's 2 tangent x. And that's what we'll get for our answer. On this one, we've got sine squared over cosine squared. Well, that's the same as sine x over cosine x, the whole thing squared, right? That's just a rule of exponents, or we call it tangent squared x, and that's a simpler way to view that one. Here's another one that comes up quite frequently, tangent x cosine x. And if we want to clean this up, we're going to go the other way, and we're going to write tangent as sine x over cosine x. That's what tangent is. And the cosines then, since we're multiplying by this cosine, the cosines will cancel, and we're left simply with sine of x. So we want to look for those kinds of things. I want to go on now with some extensions. These things don't show up in the SL syllabus, but they're worth your noting. And so I want to just show you what they are. Mathematicians have defined, because it shows up a lot, the reciprocals of the trig functions. So 1 over sine x is called cosecant, and it's spelled C-O-S-E-C-A-N-T, secant and cosecant. So cosecant x is the reciprocal of sine. If you're looking at a triangle, instead of doing the opposite over the hypotenuse, cosecant is defined as the hypotenuse over the opposite. Just flip it over. It's a reciprocal. Secant, which is this one, SEC stands for secant, and it is 1 over cosine x, the same reciprocal type of idea. And cotangent is, this is cotangent, is the reciprocal of tangent. And it's simply defined as, instead of sine over cosine, cosine over sine. Why are these worth using? Well, because there are certain relationships and equations where you get into things and the reciprocals show up a lot, and it's just faster and easier to write them as products with the reciprocals instead. Here's a couple of little exercises for you that I'll show you. I want you to pause the video and see if you can come up with an identity, starting with the Pythagorean identity, and get an identity for secant squared in terms of tangent squared and cosecant squared in terms of cotangent squared. So try that if you see what I mean, and then come back and take a look. All right, so here we are. As I said, start with the Pythagorean identity. So if we start with sine squared theta plus cosine squared theta equals 1, and we're looking for something that involves secants and tangents, well, then probably what we want to do is divide by cosine. Because if we divide by cosine squared here, we'll get tangent squared. So if we divide by cosine squared, everything on the left, divide by cosine squared, divide by cosine squared, and divide by cosine squared, we get what we're looking for, which is, here's tangent squared, now sine squared over cosine squared, tangent squared theta plus, this is 1, cosine, that's just 1, and 1 over cosine squared is secant squared. So this is another way of thinking of the Pythagorean identity, except in terms of tangents and secants. And then we can do a similar thing with cosecant squared by starting with sine squared theta plus cosine squared theta equals 1. And now if we divide by sine squared instead, we're going to get sine squared theta here, a sine squared here, and a sine squared theta here. We get 1 plus cosine squared over sine squared. That's cotangent squared. Cotangent squared theta, and that equals 1 over sine squared, which is cosecant squared. So we get these two versions of the Pythagorean identity, which are sometimes useful. Again, you're not going to see those in SL, but it's worth knowing about them. These are just the proofs of those. All right, so we're going to go on now and look at some other ideas. Okay, let's go on. This is section C.2 in the book, and what we're going to do is look at how factoring can help us to simplify trig expressions and solve equations eventually. We're still going to mostly be using this one identity, the Pythagorean identity, sine squared plus cosine squared equals 1, for most of these. So to factor, remember, is to write things in product form. And we see that this is a sum, and so we want to try to write this as a product. And if you look carefully, you may notice our old friend, the form a squared minus b squared. And remember that that is equal to a plus b times a minus b, because when we FOIL, the cross terms ab and minus ab disappear, and we just get a squared and a minus sign and b squared. So that's what we want to do here, and recognize that we can write this as cosine alpha plus sine alpha times cosine alpha minus sine alpha. And that's really what we want to. We want to see that when we have a difference of two squares like this, we can do this, and often that helps us work out a problem. Here's another example. And what we see here is tangents, but if you look carefully again, you see this quadratic form. You see kind of an x squared. If you think of tangent theta as x, there's x squared minus 3x plus 2. And so we can write this as in factored form by seeing that this is tangent theta here, tangent theta and tangent theta. Those two terms are going to give us our tangent squared. And then we need two numbers that are going to multiply to 2 and add to 3. And they're both negative, and one of them is 2 and one of them is 1. And so we get this factorization of that expression. And this will help us if we're solving, for example, an equation where this were equal to 0. If we said this had to be equal to 0, for example, then we know that either tangent theta is 1, so that this factor would be 0, or tangent theta had to be 2 to make this factor 0. So that's one of the reasons why we're doing this factoring. Well, let's take a look at this and see it in a little more complex situation. What we want to do now is simplify this. And of course, we think about how can we factor this to simplify. And one thing people see is, well, that there's a 2 here, so we could write this as 2 times 1 minus cosine squared, right? We could write it that way. 2 times 1 minus cosine squared theta, and over 1 plus cosine theta. And then we can see that the top, that 1 minus cosine squared, is sine squared, so we could write this as 2 sine squared theta over 1 plus cosine theta, right? We could go this way. But this isn't really a lot simpler. It's still got sines, cosines, it's got squares. In fact, one might argue that this one's simpler because it only has cosines. So there's some judgment to be made here about what direction do we want to go that we really consider simpler. And in this case, an alternative, instead of going this route here, when we get to this place, we can notice that 1 minus cosine squared is a difference of 2 squares, since 1 is a square. So we could, instead of going to the right here, we write this as 2 times 1 plus cosine theta times 1 minus cosine theta. And those of you who are looking ahead understand why we would do that, because here in the denominator we've got 1 plus cosine theta, and these now are factors that can cancel, and we're left with just 2 times 1 minus cosine theta. And that would be, I think most would agree, simpler than this, for sure. So watch which direction you're going. It's not always the obvious one, and you're looking for ways to reduce fractions, get rid of factors, make things simpler. That same idea I think you can see more easily here. We still have that numerator. We're not going to do much with that. Cosine theta minus sine theta doesn't really simplify it all or factor. But cosine squared minus sine squared, that's another difference of two squares like we had over here. And so we can write this as cosine theta plus sine theta times cosine theta minus sine theta. And there's a good reason to do that, and it's kind of convenient because now this whole numerator here, which is 1 factor times 1 in the numerator, can cancel with that whole term, and we're left with a 1 up here, and our final answer is just 1 over cosine theta plus sine theta. And we're done. So those are the kinds of things that we can do with factoring, and you'll see those in much more complex situations eventually, but it's something to get some practice on. So here's the homework, and we're ready to go. Hope you all have a good day, and we'll see you next time around.